Okay, welcome back for the final video for Unit 3-1. We're going to cover the last 2 pages of this unit. So what we have here is first we're going to investigate a little bit the spring equation and more generally just second order linear differential equations with constant coefficients. So recall that with this is the spring mass equation, m is the mass, b is the damping coefficient, and k is the spring constant. The roots of the characteristic polynomial are always going to be given by the quadratic formula. And under what conditions will the solutions be exponential? Well, to answer that, you really need to ask, when do I not get sines and cosines, right? Because then things become oscillatory, as we call it. And that occurs exactly when you don't get a negative under here, right? And so this is called the discriminant. Maybe you remember that way back from your high school algebra days. Really what we want to require is that the discriminant not be negative, which in math means it's greater than or equal to 0. And when do we get oscillatory functions? Well, that's exactly when the discriminant is negative. And so we can quickly actually decide here if we're going to have oscillatory motion in our solution functions. And so just by finding the discriminant. So here m is 2, b is 3, and k is 1. So what that tells me is that b squared minus 4 times 2 times 1, well, that's equal to, I think, 9 minus 8 is 1, which is positive. And so, no, I don't have oscillatory motion here. I have just exponential behavior. Okay, and then coming here, we have m is 1, b is 4, and k is 5. So b squared minus 4 times 1 times 5. Well, that's 16 minus 20 is negative 4, which is less than 0. So yes, this satisfies this condition here. The discriminant is negative, and so it will have oscillatory behavior in the solution. And now, turning to the last page, what we're going to recall where we talked about repeated real solutions, we need to now circle back to that. So we had y prime prime plus 4y prime plus 4y equals 0. And what we found was that y had to equal c1 e to the minus 2t plus c2t e to the minus 2t. Okay, well, what we're going to do is we're actually going to verify that, like, this is the right thing to do for our second function v of t. And we said we chose it to be just t itself, but let's see where that actually comes from. So you may have to go back a couple of videos to remind yourself of this. Well, what we're going to do is we're going to say, okay, let's suppose y2 has to be of the form v of t times e to the minus 2t. All right. So now let's find the derivative. I'll suppress the t notation, and I'll skip right to the answer. I'll let you verify that this is correct. But y2 prime, if I factor out e to the minus 2t when I take the derivative, I'll get like v prime minus 2v times e to the minus 2t. And then y2 double prime, again, I'll let you work this all out. I'll just run straight to the answer. And so if we take this y2 double prime, y2 prime, and y2 and run it through the equation, what that tells me is that 0, which is this, has to equal, well, these three things added together. I guess the second one is multiplied by 4, and so is the first one. And so you get e to the minus 2t v prime prime minus 4v prime plus 4v plus 4 e to the minus 2t v prime minus 2v plus 4v e to the minus 2t. And you simplify and you factor out e to the minus 2t from everything, and what you get is 0 equals e to the minus 2t times v double prime. Okay, and so what that tells us then, e to the minus 2t is never 0, and if this is going to be 0 for all t, that tells us that v double prime has to be 0 for all t values. Oh, well, that's actually a differential equation, right? V prime prime equals 0. Well, that means that v prime must have been just a constant, and then v is just ct plus d. I mean, you just take the antiderivative twice. And so you get y2 has to be v of t, which is ct plus d, times e to the minus 2t. And if you want to expand that, you can. You get ct e to the minus 2t plus de to the minus 2t. And now here's the key observation. You might be wondering, like, okay, well, this is not just t, but really, a constant times e to the minus 2t is already accounted for, right? That's, in fact, our very first sort of fundamental basic solution here. And now here, well, the constant will be captured later when we do, like, c2. So really, we can just pick here c to be 1. And so the simplest way to do this is to pick c equals 1 and d equals 0, since we're already picking up the constant e to the minus 2t, like I said earlier. And so that's just t e to the minus 2t. Right? And that's exactly what we said we should be getting when we work this all out. Okay, now coming back down to here, what we're going to show now is that this is only a solution when you have a double root. So this answer we just found will only solve a differential equation with a repeated real root when there is a repeated real root. Otherwise, doing this multiplying by t isn't going to solve the problem for us. Okay, so what we're going to do is we're going to say, okay, let's suppose that x of t has to be of the form te to the rt. Then I'll quickly find x prime. I'll let you verify, but it's e to the rt times rt plus 1. And similarly, x double prime is e to the rt times r squared t plus 2r. Okay, so go ahead and verify that. Now, if we plug this into the differential equation, what we get is that 0 has to equal, well, a e to the r squared t plus 2r plus b times e to the rt plus 1 plus c t e to the rt, right? And if you combine everything and factor out e to the rt, you have to get that 0 equals e to the rt times, I'll sort of combine a little bit here, some steps, and what you get is ar squared plus br plus c, that expression times t, plus 2ar plus b, and that expression is just a constant, right? And so again, e to the rt is never 0, so that means that this expression must be equal to 0. So let's write that down. Okay, so here's the key observation now. This is a function of t on the right-hand side, and so if this is going to be 0 always, well then certainly the coefficient of t has to be 0, right? So ar squared plus br plus c has to be 0, and furthermore the constant term, 2ar plus b, also has to be 0. The only way that's going to be, only these two conditions guarantee that the right-hand side will be 0 for all t values, which is what it has to be because it always has to equal 0 here. Right? Well, let's just go through these one by one. This right here tells us that r solves the characteristic polynomial, right? Look at ar squared plus br plus c. So that means that r has to equal minus b plus or minus the square root b squared minus 4ac all over 2a. But the second equation here, this tells us that r is equal to minus b over 2a, which if you look here, that tells us that b squared minus 4ac, well, that has to be 0, right? You have to have a discriminant of 0, right? If these two things are going to be true, then it follows that b squared minus 4ac equals 0. And that only occurs when r is a double root, right? So and that's exactly what we needed to show, right? So the only time x equals te to the rt is a good solution is when r is a double root of the characteristic polynomial. Okay. So that is the end of Unit 3-1 notes. In the next video, we'll get into Unit 3-2, where we learn about non-homogeneous second-order equations with constant coefficients.